All right, welcome back. This time we're going to go over GPT architecture and transform applications. But before we get started, hit the like button, subscribe, and share with anyone you know who's taking the AWS Machine Learning Associate exam. So, transformers power breakthroughs in natural language processing through self-attention, which captures relationships between tokens without sequential processing constraints. This flexibility enables diverse applications from chatbots to code generation, though these systems predict tokens rather than understanding correctness, making guardrails essential for enterprise deployment. So, transformation applications. Chatbots like ChatGPT require fine tuning for dialogue, memory, and turn taking. Question answering systems take questions as input and output relevant text answers. Summarization condenses large documents into concise versions. Translation maps text between languages or formats. Sentiment analysis classifies text as positive, negative, or neutral. Named entity recognition extracts and labels specific entities like people or companies. Code generation translates natural language into programming languages. Customer service automation generates responses based on past transcripts. These applications share a limitation. They predict likely next tokens based on training data, not factual accuracy or ethical considerations. This is why moderation layers and guardrails are critical for production systems. So, some GPT architecture fundamentals. GPT, or Generative Pre-trained Transformer, generates new content after pre-training on large corpora like Wikipedia and Reddit through self-supervised learning. Unlike earlier transformation or transformer variants using encoder-decoder stacks, GPT uses only decoder blocks. Each decoder block contains masked self-attention, preventing the model from seeing future tokens during training. A feed-forward neural network adding non-linearity and capacity and residual connections with layer normalization and ensuring gradient stability. These blocks stack repeatedly, creating models with hundreds of billions or trillions of parameters and variants like GPT-4. So what's the processing pipeline look like? All right, so text transformation happens through three stages. Tokenization converts text into numerical tokens using algorithms like byte pair encoding, or BPE. Indivisible becomes indivisible. The embedding layer converts each token into a high-dimensional vector where semantic similarity corresponds to spatial closeness. Positional encoding uses sinusoidal patterns to encode word order, since transformers process in parallel rather than sequentially. These three steps create the initial input vector following through GPT's decoder stack. Generation and temperature. So, at inference, GPT performs autoregressive token generation. It takes input tokens like while this course is, and predicts the next token like awesome based on softmax output, then repeats iteratively. Temperature controls randomness. 0.0 always chooses the most likely token deterministically. 0.5 provides medium creativity, and 1.0 or more produces high creativity but less stable outputs. So, self-supervised training. GPTs train via next token prediction without labeled datasets. Given the Eiffel Tower is located in Paris, the model receives the Eiffel Tower is located in as input with Paris as the target. This self-supervised approach enables training on massive internet corpora, powering models like GPT-3, GPT-4, and now GPT-5. How does this work with AWS? So while GPT is proprietary to OpenAI, Transformer architecture underpins many AWS offerings. SageMaker JumpStart and deploys and fine-tunes Hugging Face models like GPT-2, BERT, and T5. Amazon Bedrock provides access to transformer-based foundation models from Anthropic like Claude, Meta, Llama 2, Mistral, and Cohere. SageMaker training lets you train custom transformers with PyTorch or TensorFlow. Amazon Lex with Lambda builds chatbots using transformers as backends. So what's the cost structure on this? So SageMaker Studio charges by instance type and storage. JumpStart offers some free tier models, though fine-tuning incurs GPU costs. Bedrock bills per unit and output token, varying by provider and model. Trainium instances cost less per hour for large-scale training compared to traditional GPUs. So we're not going to make this because it's going to take a lot of time, but you would go to the SageMaker console, you would launch the studio, search for GP2, deploy, or you could fine-tune it with additional parameters, and then you can run your inference. At this point, you can modify the parameters and experiment with different generation behaviors. And then once deployed, you can see the outputs and judge how they'll be effective. When you're done, you delete the endpoint. When you're finished, to stop billing. And then the unused endpoints will accumulate costs, even when not actively generating text. So make sure you clean up your workspace. Finally, for the exam, remember a couple of essentials. When the questions ask about text generation, choosing models for creative applications, or understanding how large language models process sequential data, knowing GPT architecture and its transformer foundation will guide you to the correct answer. Anyways, that will be all for this time. Thank you for joining. Before you go, hit the like button, subscribe, or share with anyone you know taking the AWS Machine Learning Associate exam. Thank you, and have a good day.